Welcome. My name is Lawrence Hall, and as Director of the Berkeley Center for Theoretical Physics, I'd like to welcome you to the second in a series of special lectures sponsored by the Center. Let me tell you briefly about the Center. It's a collaboration between 8 faculty in the physics department and 3 senior scientists at the Lawrence Berkeley National Laboratory. We have a diverse but overlapping set of interests in particle physics and in early universe cosmology. And the main aim of the Center is to support graduate students and postdocs and to bring leading researchers in particle physics and cosmology to the Berkeley campus. Without more ado, let's get straight to today's lecture. Our speaker today is one of the great thinkers in theoretical physics. He has had a profound influence on the direction of particle physics for well over 30 years. Indeed, he's been at the center of many of the most exciting discoveries in particle physics during these decades, and I'd like to just briefly mention 2 of them. In 1981, with Howard Georgi, he invented the supersymmetric standard model, which is the leading theory for new particle physics for the last 20 years. The unification of the forces hint at this theory, and the big question today is whether the Large Hadron Collider will discover it. In 1998, with Nima Arkani Hamed and Gia Diwali, he invented the field of large extraspatial dimensions. This opened the eyes of many particle physicists to a whole new realm of ideas and thoughts. For example, it may allow string theory and black holes to be probed at the Large Hadron Collider. I'll leave it to him to tell us what he's been thinking about over the last decade. He's a member of the American Academy of Arts and Sciences, and he's the winner of many prestigious prizes, including the J.J. Sakurai Prize of the American Physical Society. For me, it's a great personal pleasure and honor to introduce a longtime friend and collaborator, Professor Stavros Dimopoulos.
Let me see now. Thank you very much, Lawrence. Let me see if I can live up to this introduction by saying, if I can start my computer. Okay. So it is a real pleasure to be here among so many friends and collaborators. I've been visiting Berkeley for at least 25 years now, essentially since Lawrence joined. And my visits in the last 3 years have been more frequent and more pleasant and perhaps more productive thanks to the wonderful center that you have. So I guess we should thank the donors for making the center possible and making it very active, full of young people, always full of excitement doing physics. My title, I must admit, is way too ambitious. So first of all, of course, nobody knows what 21st century physics will be like. It is also ambitious because I'm only going to have time to cover a very small fraction of all the ideas that are out there for possible new physics during the beginning of the 21st century. Now, 21st century has a hard act to follow. The 20th century was the century of physics. The beginning was marked by the invention of quantum mechanics and the theory of special relativity, 2 of the great landmarks of physics. Towards the end of the 20th century, we established the Standard Model and theoretical ideas that can explain, at least in principle, an enormous range of phenomena from the size of the whole universe to the microscopic scales. And a key ingredient for the success of science in general and physics in particular is a principle that goes back to the 14th century. It's called minimalism. Sometimes it's referred to as Occam's razor. And it's due to Friar William of Occam, around 1400, who stated in Latin, it's much more elegant. Roughly translated in science talk, it means that theories should be as simple as possible and should have the smallest number of ingredients possible. This is, in a sense, a principle of economy which led us to a theoretical picture that we have today at the very beginning of the 21st century, where our theoretical picture covers an enormous range of length scale, starting from the universe and marching down towards galaxies, stars, solar system, biology, molecules, atoms, subatomic particles. A total range of 36 orders of magnitude of phenomena can be explained with our present theoretical ideas. And as far as we know, there is no mathematical contradiction between observation and data. Now, a key tool for utilizing Occam's idea of minimality is the principle of unification. Now, unification in general means that phenomena or things that are apparently look different are really one and the same. And the simplest way to illustrate it is, in fact, with the first substantial historical example of unification, which is due to Newton. Newton pointed out that two vastly different phenomena, terrestrial gravity and celestial gravity, how an apple falls and how the moon moves around the Earth, are in fact described by one and the same theory, the universal theory of gravitation. Now, this was of tremendous importance for several reasons. First, it demonstrated that by doing experiments on our tiny planet Earth, we can learn laws and truths that are valid universally everywhere in the universe, in faraway places. Second, it demonstrated that to explain celestial phenomena, we do not need divine intervention. The scientific method that we can learn by doing experiments in our lab can be extended to the heavens, to any place in the universe. So that gave a tremendous boost to the idea of doing science, and led, of course, to the theory of gravity. This success story of unification repeated a couple of times since the time of Newton. In the 1850s, Maxwell pointed out that three apparently very different phenomena, electricity, magnetism, and light, can all be described by one set of compact equations, the equations of electromagnetism. And again, in the 1960s, the Standard Model unified the electromagnetic forces of Maxwell to the weak force, responsible, for example, for certain types of radioactivity, and led to the electroweak model. Now, the question, one of the questions of our times is whether we can unify all of the known forces of nature, the electroweak, the strong, and gravity. And this is what is at the core of theories that are called theories beyond the Standard Model, more precisely, theories beyond the Standard Model of particle physics, of present-day particle physics. Now, this is, of course, the theory that accomplishes that is still unknown. And one of the major obstacles to the unification of all forces is the relative weakness of gravity with respect to the other forces. For example, consider a hydrogen atom, proton and electron. If you compare the gravitational force between the proton and the electron to the electromagnetic force, you find that the ratio of their strengths is a chain of zeros, 40 zeros followed by 1. Okay? So the gravitational force is 40 orders of magnitude weaker than the electric force. This is a clear challenge. How can it possibly be that gravity can be unified with electricity if the gravitational force is so much weaker than the electric force? And this hierarchy problem is at the heart of many of the attempts for physics beyond the Standard Model that started from the late 70s. And some of the theories that are going to be looked for in upcoming experiments, such as the Large Hadron Collider, are going to look for theories that may possibly account for this small number. Now, I don't have time to discuss all of these theories. I will focus on one theory because it allows for very simple geometric pictures, a geometric way of understanding why such a small number may be explained. And these are the theories of large extra dimensions. Now, according to the theory of large extra dimensions, our universe, you can think of our universe as being according to the theory of large extra dimensions, our universe is like a piece of paper that is floating inside a space of extra dimensions. So here I have drawn this gray plane that I have drawn here is supposed to represent our three-dimensional space, what we normally call our universe. And this vertical direction is supposed to represent the space of new dimensions, in this case, just one new dimension. Now, in our universe, everything that we are familiar with, such as magnetism, light, atoms, people, electricity, etc., all the phenomena and objects that we are familiar with are confined to live in our three-dimensional space, in our three-dimensional universe. Except for one thing, except the force of gravity. It and it alone can spread inside the space of the extra dimensions. And in so doing, it dilutes its strength. It becomes weaker. So even though gravity and electricity or magnetism have the same strength at a fundamental level, because of this geometric difference that gravity spreads itself inside the space of the extra dimension, and magnetism and electricity do not, gravity becomes weaker, and that can account, if the extra dimensions are large enough, for the weakness of gravity relative to the other forces. So the analogy, there are several analogies. One analogy is, for example, when a river, a strong river, when it approaches its delta, it spreads into extra dimensions, into two dimensions, and loses strength. Another analogy that is useful is to consider the surface of a pool table. So the green surface of the pool table can be thought of as corresponding to our three-dimensional space. Elementary particles, the billiard balls on the pool table represent elementary particles in our three-dimensional space. And as we are familiar, when two billiard balls collide, they produce sound waves. And the sound waves they produce, they don't just propagate on the surface of the pool table, they also propagate perpendicularly to the surface into the space of the extra dimension, into the vertical dimension. So sound waves correspond to gravity in that they spread into all three dimensions, whereas the billiard balls correspond to elementary particles. They move on the surface of the pool table or in our three-dimensional universe. How will we know that such a speculative theory is correct? Well, one place where this theory can be tested is, of course, the Large Hadron Collider at CERN. And here is a picture For those of you familiar, this is the city of Geneva. This is the airport, just to get an idea of the scale. And this red ring represents the tunnel where the protons run in the Large Hadron Collider. Okay. The tunnel is about 27 kilometers long. Protons accelerate both clockwise and anti-clockwise near the speed of light. They move about 10,000 times per second around this 27-kilometer perimeter. And they collide. They are made to collide at 4 spots, these 4 yellow spots, which are the collision points of the experiment, around which there are big building-sized detectors that are looking for the particles that result from these energetic collisions. Okay? So protons collide at high energies, and they give rise to particles, hopefully some new particles, some yet to be discovered particles. And these are, of course, the initials of these experiments. And the 2 main experiments I'll be talking about is ATLAS and CMS. So, yeah. If the interior, I should say the tunnel is about 100 meters underground, and that's what the interior of the tunnel looks like, and this is where the protons move. Now here for calibration, here is the CMS detector. So you see it's a huge detector. It's about roughly, let's say, 4 stories. You see a person there just to get an idea of scale. This is the smaller of the LHC detectors. And of course, this is an old picture from when the detector was being assembled, and it's very impressively instrumented. So now this is a collision that was recorded a couple of days ago at energy of 7 TeV in the CMS detector. So the protons come from the left and the right. They collide, and they produce a spray of particles. And there is a small chance in this particular collision that there may even be hidden somewhere there a new particle that gives rise to this spray. But the intensity is not yet high enough that we can say this with any level of confidence. The LHC is an amazing machine. One can spend a whole lecture and much more talking about how amazing it is. I will just point out a few facts, very impressive facts, that it is a tremendous international effort involving 7,000 scientists from 80 countries. The proton beam has a cross-section smaller than a human hair. And at full luminosity, if you take the total amount of energy that is stored in the whole beam at any moment, that energy equals the energy of a TGV train, of a very fast train, going at 200 kilometers per hour. So a lot of energy there. You better have good control of the beam. Again, at full luminosity, it will have 1 billion collisions per second. Of course, you are not going to be recording all these collisions. You are only going to choose intelligently a small subset of them that look particularly interesting. The amount of bytes of data that would be contained in this is 10 to the 22 data per year versus 10 to the 19 bytes that are currently stored. So it's a tremendous challenge, technological challenge, to deal with this and to deal with this data flow. You have a worldwide grid. Now, how can the LHC possibly tell us anything about extra dimensions? And the first way, again, we can infer by analogy with this billiard ball, the pool table, how if we were 2-dimensional observers just doing experiments on the surface of the pool table, could we infer the existence of the extra dimension, of the 3rd dimension? And the answer is yes. If we collide the billiard balls and we compare the energy of the billiard balls just before and just after the collision, and there is a mismatch between the two, then if we find a mismatch between the two, then one possible explanation of this mismatch would be the production of a particle of energy analogous to sound wave that is propagating inside the space of the extra dimension. And the analogy here with the LHC is clear. When you collide two protons, if there is an energy deficiency between the beginning and the final energy of the event, and if that energy deficiency has the right characteristics, then you can infer that you emit particles inside the extra-dimensional space, the particles of gravity that are called gravitons. There is also other particles that you can produce at the LHC if this theory of large extra dimensions is correct. You can produce, there are other extra dimensional particles called Kaluza-Klein particles that are not necessarily associated with gravity. And there is also, if the underlying theory of gravity is string theory, you can also produce vibrating strings at the Large Hadron Collider, which as Lawrence said, this would be very exciting. This could allow a connection between experiment and string theory, and that would be one of the most exciting things that could happen in the next decade or so. Now, other signatures, other possible signature at the LHC is the production of a microblack hole. Now, this is a signature that has attracted a lot of attention, a lot of popular press. A couple of lawsuits have been filed to prevent the LHC from turning on because of the fear that black holes, because they will start eating matter, eating atoms that are next to them. And black holes have voracious appetite, so as they grow, they become bigger and bigger. And the bigger they become, the more they eat. And this can lead potentially to a runaway situation where a black hole produced in Geneva can start eating the city of Geneva and Europe and move towards the US and eat up, consume the whole Earth. So that is the famous doomsday machine scenario that was attracted a lot of popular press. And there are at least two reasons why there shouldn't be any concern about this. One is theoretical, and the other is experimental. The theoretical reason this should not be of concern is that, in fact, we understand these black holes, and we know that these black holes have very short lifetimes. There is a process called Hawking evaporation that leads them to decay so rapidly that they don't have time to move from one atom to the next. So they can at most eat one nucleus in their lifetime, and then they will rapidly decay via Hawking evaporation into a spray of normal particles. The more convincing pragmatic reason why this is not a concern is that collisions far above the LHC energy have been happening for the last 5 billion years because the universe is filled with very energetic particles that are called cosmic rays, which have been colliding with atmosphere for a very long time. And if this theory is correct, they've been producing such black holes, which have not consumed the Earth in the last 5 billion years. So no reason to worry about it. OK, so let me now summarize briefly our new worldview that is inspired by this large extra-dimensional picture. So here, this is a picture of our universe, and it is inside a space of extra dimensions. So this is just one extra dimensions. There could be 6 extra dimensions. And it's quite possible that our universe is the only universe inside this extra dimensional space. But there is no reason at all that it should be so. There is a lot of space inside the extra dimensional space. There could be, for example, 2 universes. Or there could be 3 or more. So this leads to the possibility that there are many universes, so-called parallel universes, that live or cohabitate or coexist inside the space of the extra dimensions. They are separated from each other, so the only way they communicate with each other is through the force of gravity. That's the only necessary way in which they communicate is through the force of gravity. And because gravity is a very weak force, it would be hard to be sure that such universes do not exist. And it would be fun to search for them. Now, the very possibility of the existence of many universes puts in question the idea of minimalism. And it suggests that perhaps the idea of minimalism does not apply to universes. After all, there is an alternate philosophy called the philosophy of plenitude, which has been around for a long time. The advocates of this philosophy were Leibniz, Bishop Berkeley, Immanuel Kant, and other great philosophers. And according to them, perfection in nature arises from realizing all possibilities. Sometimes this is called the principle of opulence, as you can detect by just contrasting the hairstyle of the 2 philosophers. Okay? So this tension between minimalism and plenitude is not really a new thing. It goes back to the 1600s and before. Back in 1600s, the principle of minimalism had suggested that there is in fact only one solar system. And the most important question of physics is to understand that one solar system, namely to understand the sizes of the orbits of the planets. And there were theories involving Platonic solids that were supposed to explain the distances of the then known planets from each other. And that was the central issue of physics. There was also a puzzle, a mystery associated with this, which was why is it that the Earth, the planet we live on, happens to be just the right distance away from the sun for us to exist, for us to live happily? Why isn't the Earth much closer to the sun, in which case we would boil, or much further away from the sun, in which case we would freeze to death? And why is it at just the right distance to allow for life to flourish? And of course, that could suggest, in the presence of just one solar system, some divine intervention that makes sure that this is the case. Now, as we know, in fact, there is many solar systems. There is about 10 to the 21 solar systems, so an enormous number of solar systems. And given this fact, both the physics questions that we ask and the mysteries that we have completely change. For example, given that there are 10 to the 21 solar systems, the question of what is the distance of any given planet from the center of its star, from the center of the sun, is not a very interesting question. It's just a historic accident. There is all distances are realized or scanned in the universe. All planet-sun distances are realized. And also, the previous mystery that I advocated is also not there. the statement that you no longer need divine intervention to explain why there is a planet at just the right position for life to flourish. Now, this idea seems, of course, obvious to us, and we may find it humorous that people were arguing about this. However, back in 1600s, it was somewhat more controversial. And in particular, it led to the demise of the philosopher or the thinker, Giordano Bruno, that proposed this idea. This was one of these very heretical ideas that was suggesting that we are not unique, that our solar system is not unique. And so to summarize, having a plenitude of solar systems, having many solar systems, is very important for two reasons. First, it changes the physics questions that we consider important, the way we think about our solar system. Secondly, it points to what's called environmental selection within our universe. That within our universe, the Earth-Sun distance is not a mystery. We, by necessity, will live in an environment that allows us to live, to flourish. And this is an uncontroversial application of what's called the principle of environmental selection, or the anthropic principle. Now, a natural question to ask is, could history repeat itself? Could it be that our universe doesn't obey the principle of minimalism? It's not alone, but our universe is nothing but one small component of an enormous multiverse of many different parallel universes scattered inside the space of extra dimensions. And string theory suggests that the answer to this question is yes, that string theory seems to suggest that when it comes to universes, the philosophy of plenitude is favored. The way the argument works is as follows. Now, as you may know, string theory, mathematical consistency forces string theory to have 9 spatial dimensions, not just the 3 familiar dimensions, but an extra 6-dimensional space. And this picture here represents this point of view. So this plane here represents our 3-dimensional universe. And the sphere represents the 6-dimensional space of extra dimensions that exist in string theory. And of course, the 6-dimensional space can be something very simple, like the sphere that I have drawn, or it can be a bit more complicated. It can be like a donut, or it can be a double donut, or it can be much more complicated. It can have many, many holes. And depending on the shape of the extra dimensions, the physics, the laws of nature that we obtain in this 3-dimensional space that we can call a universe are vastly different. For example, the types of particles that you get in this 3-dimensional space, the forces that you get in this 3-dimensional space can be vastly different depending on the shape of the 6-dimensional space. In particular, therefore, all the laws of nature can vary depending on the shape of this extra 6-dimensional space. So extra dimensions in string theory imply a plenitude of possible universes, and the laws of nature depend on the shape of the extra dimensions. In particular, the amount of energy in the universe depends on the 6-dimensional, on the shape of the 6-dimensional space. Okay. Now, it turns out that the energy of the most universes, represented here by these gray colors, most universes, is so large that it blows galaxies apart. And our universe, that is represented here by the only plane that has some light in it, is absolutely unique in having a small amount of energy. So if the energy of a universe is very large, as it happens for the majority of them, the vast majority of them, then galaxies do not exist. If there are no galaxies, there is no light, there is no planets, there is no stars, there is no people, because we live on planets and we draw our energy from stars. So universes without galaxies are uninhabitable and inhospitable places. So the vast majority of the universes are uninhabitable. They have no observers. They have no galaxies, no observers. So our universe is very rare in having such a small amount of energy that it doesn't blow the galaxies apart, and it allows for stars, planets, and eventually life to form. And this comes under the heading, this is an extremely famous problem of physics that has been concerning physicists for many decades. It's called the cosmological constant problem. How come the energy of the universe is so small to allow for galaxies and therefore life to form? Now, if you adopt the principle of minimalism and you believe that there is just one universe, then again you have to believe in some analog of divine intervention, that there is some not all understood mechanism that allows for the energy of the universe to be small enough for galaxies to exist. If you adopt the principle of plenitude that is suggested by string theory, then the question of whether there is any universe in which life can form is just a matter of whether you have enough universes available so that some of them, at least some of them, have energy density small enough for galaxies to form. So the question becomes one of environmental selection. So this is, in a sense, the very existence of galaxies is an experimental or an observational argument in favor of a plenitude of universes, just as the string theoretic argument was a theoretical argument for the existence of a plenitude of galaxies, or a plenitude of universes, I'm sorry. Now, how do we look for other universes? That is a very challenging question. Galileo, of course, was very fortunate. Galileo invented the telescope, and that allowed us to directly look for other solar systems and prove that there is more than just our one solar system. Is there an analog to Galileo's telescope that allows us to look at other universes? And the answer is, of course, the answer is no. There is nothing as simple as Galileo's telescope that we have yet thought about that we could use to look for evidence of other universes. But there are a lot of clever ideas about possible indirect evidence for other universes. And one I've already discussed is the very existence of galaxies. There is another theory that I called split supersymmetry, which is also inspired by the possibility of the existence of many universes. And I don't have time to describe it, but I'll describe just one of the very interesting experimental consequences that it has. And then there is a very recent observation that a plenitude of universes also is strong evidence than a plenitude for a plenitude of new particles in our own universe that we could experiment with and see directly. In other words, the very same string theory ingredients that gave rise to to many universes also give rise to many new particles that with specific properties that we can look for and observationally probe this idea. So let me first give you just a very brief experimental consequence of split supersymmetry at the Large Hadron Collider, and then I'll give you a brief overview of observational ways of looking for a plenitude of particles in our universe. So in the theory of split supersymmetry, it turns out there are some long-lived particles that will be produced at the Large Hadron Collider with some quite unusual properties. And the unusual property is, in fact, first, their longevity, and second, that they can be captured inside the LHC detectors. So if you here is two protons colliding at the Large Hadron Collider. They produce these two new particles, these black dots, which have a name. They're called gluinos, and they stop inside the Large Hadron Collider. And they have very long lifetimes. How long? We cannot compute. They can, we know that they are long. It can be hours, days, weeks, months, much, much longer than a typical elementary particle. So you can wait for days or weeks or perhaps months. And one day when you least expect it and when no one is looking because they are on vacation, these particles decay. But nevertheless, the detector is not on vacation and can detect the decay products. This is a very unusual signature that could be a probe of, it's one of the probes of this theory of split supersymmetry that would constitute evidence for the multitude of universes. Now, the signature of, as I was saying before, the same ingredients that give you a plenitude of universes also gives you a plenitude of particles, and they have a variety of signatures. They influence the light, the first light from the Big Bang in unique ways. They influence the way the matter is distributed in the universe. They give rise to long-lived particles at the Large Hadron Collider. I mentioned before, and there are new particles that do the same. And perhaps most exciting, they affect the evolution of rotating astrophysical black holes in ways that can be detected in future experiments. So if you have, here is a black hole. So here is a black hole that's rotating very, very rapidly. The rotation of the black holes produces a cloud of these new particles. They have a name. They're called axions. So a cloud of these new particles. And this cloud, in turn, emits gravitational waves that can be picked up by either present or future gravity wave detectors, advanced LIGO or LISA or AGES. And these particles have distinct characteristics. So the philosophical debate between minimalism and plenitude is several hundred years old, and it continues. in the near future, in the next decade or so, we will start having a plenitude of experiments that can probe this question, both laboratory experiments such as the LHC and several astrophysical experiments that will probe this question. So what in the 16th century, the question of whether there is one solar system or many solar systems was a philosophical question. Thanks to Galileo's telescope, it became an observational question, and it was resolved in favor of the plenitude. What we are hoping for is that in the 21st century, the idea of whether there are many universes or one universe is also becoming a question that will be subjected to observation. And many theorists are working on ways to probe this hypothesis. So if you trace what has been going on from ancient times to now, we started out in ancient times by thinking that the Earth is at the center of the universe. Then we demoted ourselves, and we said, well, we're not quite at the center, but the sun is at the center of the universe. And then we kept demoting ourselves further and further. And we said, well, our solar system is not really unique because it's not at the center of the galaxy. Our galaxy is not really unique because it's not at the center of the universe, because there is no center to the universe. And now we are entertaining the idea that our whole universe is nothing but a speck of dust in a vast multiverse. Thank you.
Thank you very much for a really great exposition of these amazing ideas. We have some time for some questions. Paul.
Thomas, what experimental result could be obtained that would disprove your idea of the multiverse?
So one idea, in fact, this is a very interesting question, but I cannot see you, Bob. Okay, so let me. It's interesting. So as you know, this whole idea in connection with the cosmological constant problem, this whole sort of anthropic reasoning, goes back to a 1987 paper of Weinberg, which answers your question. So for example, back then, back in 87, we did not know what the energy of the universe was. And Weinberg argued that when we go and measure it, if we find it to be much smaller than the maximum amount that can support galaxies, then that would be evidence against this anthropic reasoning, which relies on the existence of a multitude of universes. And in fact, in his original paper was very much along the lines that he wanted to disprove. He wanted a way to disprove the hypothesis that there are many universes. He wanted to disprove this environmental or anthropic reasoning. Then what happened, of course, as people know, is in the 90s, the cosmological constant was measured, the energy of the vacuum was measured, and it was found to be near the maximum amount that would tolerate, that would allow for galaxies to form. And that was the first indication for the contrary. So this is a spectacular example that a way it could have gone, wrong. So when, well, the rest will get a little technical. So if we feel very far, if we can prove that we live very far away from what are called critical boundaries, anthropic boundaries, then that in general is perceived as evidence against the anthropic reasoning or the reasoning for the multitude. Conversely, you can ask me what would convince me that this reasoning is correct, which is another excellent question. So let me tell you. Because, of course, since I spent a little time on it, I've struggled with this. These are very difficult questions. So I'll give you a scenario which may materialize in 20, 30 years. Let's say the Large Hadron Collider turns on and eventually gets strong evidence for split supersymmetry. The International Linear Collider or some high-energy plus or minus machine turns on, measures the coupling constants, the 5 Yukawa couplings of the theory of split supersymmetry, and finds them to converge and determine the supersymmetry breaking scale to be some large number, but much bigger than the weak interaction scale. Then there is other indicators. There may be curvature in the universe or anisotropies in the universe, or Axiverse, that we discover lots of these plenitude of particles, 2, 3, 4 axion-like particles, 2, 3, 4 new gauginos. A collection of phenomena. It's very common in science that no one fact convinces you, but it will be a collection of data together that can point to this, that there is something to this topological complexity of the extra-dimensional manifold, that it is not silent, that it gives low-energy observable signatures. And it will only be a collection of such facts that will convince us that this is true. But I started out very much as a skeptic that, well, these ideas can't be really proven. But I think over a long enough time scale, maybe too long for me, there is a reasonable chance that we may be driven in this way. By the way, well, I don't want to get into it, but yeah, that's plenty for.
Other questions? Yes, I see.
Going back to the original large extra dimension theory, what mechanism is confining our particles on our frame?
Okay, so there is. This is a very nice technical question. So you can think of analogs. First of all, I could just say, well, in string theory, there is naturally objects that are confined on brains, on what are called D brains. The best I can do beyond this is to point out that you can have analogs of confinement on, just like confinement confines quarks inside hadrons and doesn't let them separate from each other too much. You can have analog mechanisms on surfaces or three-dimensional spaces, where if a particle tries to take an excursion too far away from a three-dimensional plane, a three-dimensional space, into the space of the extra dimension, it gets pulled back by some sort of a string back into the plane. The one force for which this is hard to do is gravity. And the reason is gravity defines space. So wherever there is space, gravity goes. But and other forces other than gravity, or particles other than the gravitational particles, are easy to confine on subsurfaces by a higher dimensional extension of confinement mechanism.
Is that a new gauge field that you?
Yeah, you can do it with gauge fields. You can confine gauge fields by this. You can confine, you can confine fermions. You can confine scalars. The graviton is the one that is universal, that goes everywhere. Wherever there is space, gravity goes.
Other questions? Yes.
Yes. Another possible model that people proposed is that when we calculate the value of the fine structure constant, and then it would be an argument against it just being by chance. That does require some duality in the way we look at the universe, sort of equivalent to wave-particle duality, because it essentially is in the large numbers hypothesis, which says that you can calculate valued despite the evolution of the universe. So there's two ways to look at the universe. One is expanding from a Big Bang, and another one that is always constant. That requires a number of other things to take place. Have you looked at that argument?
No, I'm not sure I understand the question. So we have strong evidence that the universe is an expanding universe. So from...
Well, a large number is hypotheses. People say, well,
Yeah.
there's an alternative
Yeah.
way of looking at it, just like you can look at things like waves and particles. So that at least that gives a forum. I mean, their theories could be disproven, so there should be more of a dialogue here.
So what is your question?
Well, have you looked at that? I mean, have you engaged in that
No.
particular dialogue?
I mean, the large, okay, there is something, okay, so the one thing that I'm familiar with as far as the possibility that some of the small numbers in nature, like the ratio of the proton mass to the gravitational coupling constant, the smallness of the gravitational coupling constant of the protons, say, or of atoms, in the old days, great people like Dirac suggested that maybe the smallness of this number is correlated with the longevity of the universe. Okay. Now that idea has been disproven by observation, because it would suggest that fundamental constants have varied a lot, let's say, between the first moments of the Big Bang, between the time of nucleosynthesis and now.
His model is
Let's go for one more question, because I think I saw another question over here.
Is there any theory or speculation about what sort of physical laws would be extant in these hypothetical conditions?
What sort of physical laws would be valid?
Would exist?
Would exist. It's anything goes. For example, there could be universes where the spectrum of elementary particles is completely different. There could be than ours. For example, a simple change that would make a huge difference. I'll give you an example. There could be a universe which is just like ours, but the photon has a mass. So a photon has some, not necessarily terribly large mass, but a mass like like the W boson, the mediator of weak interactions, has a mass. That would be a completely different universe, because the photon is such an important particle. It allows for atoms to bind. Atoms are important for life, etc. But anything goes. The one thing that is fairly universal about all these other universes is that they have very large energy in them. Typically, they have energy which is 10 to the 120 times the energy of our universe. So 1 and 120 zeros. So that is the typical value of the energy of the universes, of any of the other universes, is vastly bigger than our own, and that is why they don't have galaxies. As far as the elementary particle theory that is valid inside them, anything goes. But they are extremely unlikely to have anything like galaxies or structures. So there'll be vast empty structures, and for the most part.
Another question, yes. Now.
So, haven't you worried that this approach, where we are saying that the physical laws are random because we cannot understand them, is the end of science?
No, that's what I'm trying to prove. That it is not necessarily the end. It's a completely different approach. So I can answer by historical analogy. Again, at the time, around the 1600s, people thought that the fundamental questions of science are to understand the sizes of planetary orbits. And many people were attached to this as being the fundamental question. The whole theory of Platonic solids and to explain planetary trajectories was invented. And then there was people like poor Giordano Bruno, who started speculating, well, maybe we're not unique. Maybe anything goes. There are all kinds of solar systems. And These are not important questions. We should ask different questions. And what we are trying to do, struggling to do, and it's only the very, very beginning, is to find what would be possible different questions to ask. And along these lines, for example, Lawrence has thought a lot about the following question, which is analogous to these sizes of the orbits of the Earth. Could it be that quark masses, the light quark masses, up masses and down quark masses, the electron mass, could it be that they are determined by environmental selection? Because if they were any different, there wouldn't be atoms, so there wouldn't be nuclei, therefore there wouldn't be normal chemistry, etc. So there is an attempt to try to make predictions or even postdictions about the known masses of known elementary particles based on these considerations. And well, that is one of the major approaches which has proven to some degree and could prove more fruitful. And what I pointed out here is, for example, the possibility of having multiple new particles with specific properties is a very unique prediction of this framework. This framework would predict tens of axion-like particles or several photini-like particles. And if you saw tens or hundreds of axions, you would be hard-pressed to not start thinking that, well, there must be some complex topology. There must be a reason for this. It's not just there for no reason.
One last question. Come to you.
So if the multi-universe is correct, does it mean that the law of gravity is invariant throughout all this universe?
Yes. So the law of gravity, for example, if there are parallel universes, okay, yeah. If there are parallel universes, yes, the law of gravity is the same. Of course, it's higher dimensional. You have to extend the law of gravitation to higher dimensions from 4 to 10, but the fundamental principles for gravity remain the same. And also, anyway, the way the various parallel universes interact, it is the one law that permeates from one parallel brane to the next to the next. So we can feel the gravity of another parallel universe that, let's say, it's 5 layers away or some distance away. Whereas we may not directly see the elementary particles that live in these parallel universes, the other elementary particles, but gravity permeates everywhere. Because it comes from because it comes from geometry. It's just that there is space, there is gravity. Go ahead.
Well, we began with gravity. I think it was Newton, is that right?
Exactly.
We go in with gravity. Let's thank Savas for a really great lecture.